To give you a brief introduction, the topic we're tackling is lung auscultation, which requires clinicians to make subjective decisions by listening to breathing sounds. This process is utilized for diagnosing a series of lung pathologies. However, it is a very subjective process. With this project, we're aiming to create a sound classification model that can standardize lung auscultation. And our goal would be to identify the crackles and wheezes from audio files or breathing to help us to build a model that is capable of aiding in the diagnosis of patients by leveraging machine learning and data analytics tactics. So the methods. First of all, we're using the CNN method, which is highly efficient in extracting spatial hierarchies of features from data, making it ideal for processing spectrograms or MFCCs derived from lung sounds. Secondly, we're using RNN, which is great for processing sequential and time series data due to being able to process the temporal dynamics and long-term dependencies in lung sounds. Combining the results of both models and looking at them individually would enable us to leverage the spatial feature detection prowess of CNN and the temporal pattern recognition capabilities of RNN. A dual approach would provide us a very comprehensive and accurate tool to give to clinicians or help clinicians utilize in the diagnosis of lung pathologies. For CNN, we first need to pre-process the data to spectrograms and for as an input. Following this, we can design CNN architecture with convolutional pooling and fully connected layers. After this, we can use the spatial feature detection for CNN in order to detect the crackles and wheezes. After this, we can train the CNN model using the pre-processed data and the corresponding labels through the use of Bragg purification and an appropriate optimizer. Lastly, we can finally apply regulation techniques and hyperparameter tuning to prevent overfitting and optimize the performance of the model. Moving on to RNN. Start off in a similar way. We pre-process the audio data and we consider normalization. We will then utilize layers for handling time series data such as LSTM or GRU. Following this, we incorporate dropout layers to prevent overfitting. And after this, we can experiment with different architectures for optimal pattern recognition. Lastly, we can evaluate the trained RNN model on the test set and compare its performance with the CNN model. So for feature extraction, we're using three main methods over here. Three main methods over here. First is the MEL spectrogram. This is very effective in the sense that it mimics human hearing perception by adjusting relative frequencies differences to match human interpretation. It also reduces dimensionality through binning and MEL bands. Furthermore, it filters out frequencies causing noise in the original recording. The second feature extraction method we're using is the MFCC, which captures power spectrum of sound in a concise manner. It is also more robust to noise and variations in audio signals. This makes it amazing for a sound classification task such as the one we're trying to implement. The third one we're using is the STFT, which analyzes both stationary and non-stationary signals, which captures frequency and phase information. This makes it very effective for a sound classification task such as the one we are doing, due to its use in signal processing for time frequency analysis. So, what we're essentially doing after this is we're also going to combine all these three feature sets into a dense feature. To do this, we'll utilize techniques such as PCA to reduce the dimensionality. We will also ensure all features contribute equally by normalizing the combined feature set. This dense feature set will be fed to CNN and RNN for sound classification. So, what are the data metrics we're using to collect the data? One of them is the F1 score. This gives a normal range of respiratory. Given the normal range of respiratory patterns, F1 score is a very suitable metric over here. It is especially great for imbalanced data sets with varying costs associated with false positives and false negatives. As we see from the equation on the right, by taking into precision and recall, it tackles this issue very well. Secondly, to find a loss function, we're using the sparse categorical cross-entropy method. This is very suitable for multi-class categorization scenarios and evaluates accuracy by comparing ground truth against predicted probability distribution, which we can see in the equation on the right. So what are the steps we're following? So first, we're importing the data and making a data frame, as you can see on the right in the first image on top. After this, we'll pre-process the data and split the audio into cycles and update the data frame. We chose 6 seconds as the standard length here, as about 98% of cycles are less than 6 seconds long, as you can see in the image on the right in the middle. Thirdly, we will categorize the data and then divide it. So as you can see on the right, we have categories such as such as data that yielded crackles, wheezes, both or none of them. We then made CNN and RNN models for the different features, which we can observe over here. And this step also creates a dense network combining all three, and then we'll also combine all three features into a singular RNN and CNN model. So this is what we trained the model on. We initially trained the model on the individual feature sets, but this is what I'm going to show you is the result of all the dense feature sets for the CNN model. As you can see over here, that it yielded accuracy of almost 69% and a loss of 0.82. Compare this to the dense RNN model. As you can see, it had a very low accuracy, only 56%, and a much higher loss rate of over 1. And an ideal model should have a high accuracy and a low loss rate. If you look on the right, you'll notice that for the category with both, we actually don't see anything, and I will explain this later. This is when in this slide where we essentially found the results if we combine the dense CNN and the dense RNN. Although we see a higher accuracy of about 71%, the loss is actually higher as well. So which we will need to factor in when picking which model we want to go with. All right, so giving you guys a summary of our results, we see this RNN. We can see in the video in our final report, which I don't have in this video currently, but the RNN and CNN perform very similarly if you compare individual feature set data, with about 50 to 60% accuracy about across all individual features. However, if you take into account the dense CNN, which takes into account all the feature sets, it heavily outperforms the dense RNN, with about a 68% accuracy compared to RNN only having a 56% accuracy. And if you use the combined dense set versus the dense CNN set, we see very similar accuracy, close to 70%, and with 68% come from dense CNN, and the combined one being just under 71%. So how do we identify the best model moving forward? With RNN, we can clearly see we face challenges with overfitting due to the insufficient number of samples with Krackels and Wheezes, and trying to oversample resulted in skew data. This is actually the reason why earlier we did not see any data for the both column. The dense RNN has a very low accuracy and high loss, which suggests that CNN is much more suitable than dense RNN for audio classification model. Now, how do we choose between the dense CNN and the dense combined set? So we noticed that the dense combined set had lower performance, and it actually yielded higher losses than dense CNN, even though it had just a slightly higher accuracy of about 2% higher. As a result, we went forward with the dense CNN as the most reliable and consistent method for this project. So, where do we go from here, or how can we further improve the model from here? First of all, we need to look at we need to look at overfitting for unbalanced data. The challenge we had is we did not yield the desired results, and we had distortion in oversampled data. A proposed approach could be to employ synthetic overfitting, which would give a more balanced data set and improve learning from underrepresented classes. The second way we can improve is a hyperparameter tuning. This is crucial for optimizing model performance, and it is very impactful in deep learning models such as the two we used. We can also this will help us to fine tune the model for enhanced performance. Lastly, we can use enhanced data cleaning and pre-processing. This is critical for model improvement, and the technique we want to use is we want to refine data cleaning considering advanced techniques like data smoothing.